The last problem we'll look at in this series has to do with an optimization problem in one variable where we optimize the total cost. So let's read the problem. So as you see, there are two costs: the initial cost, the construction cost, which is constant, it's not random, and a failure cost. This failure cost is actually a random variable. It's a binary random variable. It can have two possible values. If everything goes all right, there is no failure cost. But if there is failure, then it's quite a huge cost, 10 to the power 4 crore rupees. So when we want to find the expected value of the total cost, CI is a constant, so it remains as such. But the expected value of the failure cost now looks at the two possibilities. So it's 10 to the power 4 times PF and 0 times 1 minus PF. So if you put in the values of CI and PF in terms of the resource X, then we have an objective function which we can minimize using any standard method. And if you do it right, then you should get the answer of about 17,300 tons would be the optimal resource to spend, and the corresponding value of the initial cost would be about 875 crore rupees, and the optimal failure probability for using that amount of resource would be 0.0056. So that's a nice optimization problem that can be solved. But here is an interesting question, is that what if this cost-based optimization solution is not acceptable to the regulators? The regulators might have other considerations for setting a value of, in this example, say 0.0001, that comes from considerations other than minimizing the total cost on behalf of the owner. And so your original answer of 0.0056 is too high. That amount of failure probability is not acceptable. So in that case, we have to revise the answer. So that would give us an X star of almost 21,000 tons. So going up from 17,300 is 21,000 tons. And obviously, it will cost somewhat more. Instead of 876, it would cost almost 200 crore rupees more, so about 1,058 crore rupees. So that would be the revised answer. Now, I want to also bring out one interesting feature which is present in such problems, and for that we need to look at the graph of the costs. So what you see on the x-axis is the resource that we have, X, the steel in ton, and then we have three graphs. The blue graph is the linear construction cost. The orange curve is the expected failure cost, so that is PF times CF, and PF decreases with increasing X. And the yellow curve, which is the sum of the two, the sum of the blue and the orange, so that is the total expected cost. Now, the optimization that we did in the first, which gave us about 17,300 tons, that would be the lowest value of the yellow curve. Now, in such problems, you'll see that the cost is not symmetric. So if you move to the left of the optimal point, of that optimal point of 70,300, there's a much steeper rise than if you moved to the right of the optimal point. It's a much more gentle rise. So there is a case for here to err on the side of caution. So if you have to, if there are uncertainties, if some error has been made inadvertently, then it's probably much safer to spend a little more, to employ a little more resource, because the consequence is very unsymmetric.